The mixing of columns is described in chapter 5.1.3 of the specification, and it is one of the more mathy chapters of the specification. The mixing of columns takes columns of the internal state and considers these columns to be 4-term polynomials in the Galois field 2 to the power of 8, meaning that each byte of a column of the internal state is seen as a coefficient to a polynomial of degree 3. Each column polynomial is then multiplied with the fixed polynomial a, described in 5.5, and the specification did a good job at describing how this multiplication then transforms a column. The least significant byte is replaced by this first calculation, which is a triple XOR, and with the first term being the multiplication of polynomials of degree 8 as described in chapter 4.2 of the specification. Chapter 4.2.1 then defines a very useful x-time function that can be used to calculate the multiplication of 8-degree polynomials with x, where x is represented by a byte of value 2. This we will need a lot in order to calculate the mixing of columns, as we can see from the spelled out matrix multiplication in chapter 5.1.3. Implementing the mixing of column then completes the AES encryption cipher. The AES decryption cipher is described in chapter 5.3 of the specification, with pseudocode outlined in figure 12. This AES decryption cipher is essentially the inverse of the encryption cipher, and as such, the implementation of this decryption cipher will not explicitly be demonstrated, as many of the ideas can be taken over from the implementation of the encryption cipher. However, it's now time to see how I implemented the last missing mixing of columns function, which then completed the overall implementation of the AES encryption cipher. Knowing from chapter 5.1.3 of the definition of the column mixing function that this function transforms columns of the internal state, this translates to our mixing of columns to be a transformation of the rows, as our internal state is a transpose of the internal state described in this specification. In order to avoid having to implement 8-degree polynomial multiplication myself, and to be able to fall back on the x-time function provided in chapter 4.2.1 of the specification, I had to reformulate the equations given by the matrix multiplication 5.6 of the specification. The first least significant byte of a row is the triple XOR, with the first term of this XOR being the multiplication of x with the first byte of the row, and the second term being the multiplication of x plus 1 with the second byte of the row. For the first term, I could reuse the x-time function defined by the specification. For the second term, I had to first extract the second term out into an additional XOR, which I could do due to x plus 1 times s being x times s plus s. Undoing the distribution of CO and C1 then led me to a quite simple expression for the first byte of the row. For the remaining bytes of the row, I could proceed along the same lines. Finishing this off, I realized I can simplify further by first calculating an all XOR and then each byte just contributing with an XOR to cancel its byte out in the all XOR. And last, I had to preserve the 0 byte as it's overwritten at the beginning, but its value also used for the substitution of the 4th byte. Left to implement was the xtime function defined in chapter 4.2.1, which specifies that the multiplication with x really is just a shift left, with an XOR of 1b in case the shift left leads to an overflow into a 9-degree polynomial. With this, the NIST-based test cases for the AES encryption cipher then finally passed.